Like was said, my name's Bronson Messer. I guess in the spirit of everybody else who's gotten up, I should give a little bit of background about myself, and I've tried to encapsulate it here in my various affiliations. I have too many. I'm currently the acting group leader for a group called the Scientific Computing Group at the Oak Ridge Leadership Computing Facility. And in keeping with our local environs, my group, the Scientific Computing Group, is made up of PhD level scientists in all the various computational domains that we typically see at Oak Ridge. You could liken us to the staff scientists that are just down the road at the National Optical Observatories. We have some part of our time that's devoted to our own research, but we're there to make sure that the scientific program that's carried out by the center is also carried out. I'm also matrixed into the theoretical astrophysics group at Oak Ridge, and I have an affiliation with the Department of Physics and Astronomy at UT, mostly so I can seduce graduate students into doing this sort of work. So I've laid out too ambitious a program for myself for the talk. I'm going to, as Don alluded to, tell you a little bit about the other kind of supernovae, actually the ones that are more prevalent both in number and in type, so-called core collapse supernovae. And I'm going to try to convince you that just like what we heard about thermonuclear supernovae and what we heard earlier about galaxy formation and evolution, that this is a prototypical, an exemplar of multi-scale, multi-physics simulation. I will posit the notion and let people argue about it. That is perhaps the hardest computational problem that we undertake, certainly at the OLCF. And considering we're the biggest computing center on the face of the earth, I think that's a pretty good advertisement. Hopefully at the end I'll have time to make a bunch of provocative statements without proof, assail you with opinion, but also provide you with a handful of observations. So first, I love this Scientific American article about blowing up supernovae. That came from 2006. The title, the article is great, Catastrophes, what makes a star blow up. How to blow up a star is the name of the article itself. When you get in there, it only gets better when you actually get to the lead. The first sentence is, it's not as easy as you would think. And having tried to blow up stars for way too long now, I can assure you that actually is the truth. So what kind of stars am I talking about blowing up? Well, they're significantly different than the stars that Don just told you about. So the end point of stellar evolution for our own sun will be a white dwarf, and perhaps if our sun were in a binary system, it could hope to end its life in a spectacular type 1a explosion. The kind of stars that undergo core collapse are massive stars, typically stars that are 8 or more times the size of our own sun. These stars are really different from the sun in as much as instead of living for billions of years, the sun's been around for roughly 5 billion years, it'll be around for another 10 to 15 more, they live fast, die young, and leave a heck of a corpse. So a 17 solar mass star, in opposition to what the sun will go through, will only live about 10 million years before it exhausts the entirety of its nuclear fuel. The interesting thing about these very massive stars is everybody knows what makes the sun shine. Basically, it's the release of energy from nuclear fusion, that is fusing hydrogen nuclei into heavier and heavier elements. Massive stars can take the ashes of that hydrogen burning, helium, burn it to carbon, burn the carbon to intermediate mass elements like silicon. It can burn the silicon to iron, and then the star is out of luck. Because iron sits at the top of the curve of binding energy, you can't take an iron nucleus, slam them together and get energy out. So what you end up with is a star that looks sort of like this. It looks, the usual pedagogical lie is that it looks like an onion. It has an iron core surrounded by a shell of silicon, surrounded by successively lighter shells as you go out. That iron core, remember, is not generating its own heat source, its own energy source. It's only being held up by what's called electron degeneracy pressure, which is also the same thing that holds a white dwarf up. So if everybody took high school chemistry, remember the Pauli exclusion principle about how you have to fill up successive energy levels in an atom? Well, imagine a macroscopic, several thousand kilometer object that's held up just by the 0 point energy of having to stack those electrons up. There's a limit to how much you can hold up against self-gravity, against that with that sort of force, and it's called the Chandrasekhar limit. It's about 1.4 solar masses. So once that iron core gets that big, it collapses in on itself. It collapses in on itself with infall velocities that approach about 70% the speed of light. You take an object that was originally about 10,000 kilometers in size, squeeze it down to 60 or 70 kilometers in size in about a tenth of a second. When you take that much mass, squeeze it into that small of a volume, the density goes up. And it goes up to several times what's called nuclear matter density, which is not the density of lead or osmium or platinum or something that's nice and heavy, but is in fact the density of the atomic nucleus itself. It's 2.4 times 10 to the 14 grams per cubic centimeter. So a cubic centimeter is about the size of a sugar cube. If I had a sugar cube of nuclear matter density here on the surface of the Earth, it would weigh as much as all of us. And when I say all of us, I don't mean all of us here in the room, all of us here in Tucson, all of us here in Arizona. I mean all of us humans. It would weigh as much as the entire human race. Needless to say, when matter gets that dense, it desperately does not want to be squeezed anymore. So it's like taking one of those nice cheap Nerf balls, squeezing it in your hand. There's a change of state. Suddenly, when you squeezed all the air out and it rebounds into your hand. The same thing happens with the inner part of the star, and it's the shock wave that's formed by that rebounding that will eventually rip the star apart and produce what we see physically as a core collapse supernova. It's been known for a long time that the shock gets born this way and starts to propagate out, but that it stalls at some point. It's like taking a plow, walking out to a field, shoving it and hoping that it's going to go to the end of the row. Guess what? It won't. It's expending energy, tearing the soil apart. The same thing happens with the shock wave. You stall at some standoff distance. The hope is that the prodigious amount of energy that's coming off this hot central object, this thing that you've shocked by pressing it so hard, will eventually re-energize the shock and get it moving outward in radius. And you can actually do, and upwards of a decade ago, we actually did some simulations of this in spherical symmetry on small workstation type computers. Actually, at the time, it was a Cray J90. You can do it on a workstation now. Just look at the top frame, which is the velocity, and you'll actually see the shock forming. Oh. There's shock formation. It goes through something called the neutrino spheres, and that robs of energy. Now it's what's called an accretion shock. So there's no positive velocities, but you are slowing matter down as it goes in. But you can see it's still moving out. Then it gets to some stall distance, but now hopefully this neutrino reheating paradigm will happen where this central object reheats things and gets it moving. But it's still slipping back into the potential well. It's still slipping back. At this point, you're scared they're not going to let you graduate. It's still slipping back. And nevertheless, this null result was important because what we discovered is we can't explode core collapse supernovae in spherical symmetry. But that's okay, and this is a recurring leitmotif in this story. That's okay, there's something else we can turn to because there's plenty more physics that can be explored, and especially in multi-dimensions. We know that in general that there will be convective heating from below inside what is the protoneutron star. Out near this standing shock, there's going to be convection that you can't capture when you do a spherically symmetric simulation. In general, stars have magnetic fields. In general, they rotate. There's also something else here. So we need 3D models that can handle all of this physics, and that's where this notion that core collapse supernova simulation is the very apotheosis of multiphysics modeling comes in. You really need good models for all of these processes with high physical fidelity if you want to hope to be able to make qualitative and quantitative statements about what actually happens in the explosion mechanism. So along with all the things that I listed, having a good gravity solver, having a good way to calculate neutrino heating, which it turns out is very hard indeed. It's like radiation transport in a nuclear reactor, but you have widely disparate mean-free paths. Neutrinos act much differently than neutrons, for example. Convection, nuclear burning, but you also have what's called the shock instability. So it turns out that if you look at that stalled shock at some point, but you look at it in multi-D, any standing accretion shock like that is unstable to small perturbations. And you'll finally, and in 2D, for example, you'll get this sloshing mode back and forth. The sloshing mode serves to push the shock out. This was first observed in simulations of black hole accretion flows, but it wasn't recognized as such. Now there are lots of simulations of core collapse supernovae that show this sort of behavior. There's also a recent paper by Flagiso et al. Where they take a water table and basically can reproduce the standing accretion shock instability on a small water table because the shallow water equations, it turns out, act a lot like the simplified equations that were used to perform this simulation. The most important thing to me here is that this standing accretion shock instability was discovered computationally. It was one of the biggest projects that was undertaken on the Cray X1E at Oak Ridge before we sort of switched over to the XK or XT series of Crays, and was one of the DOE breakthroughs of the decade for the first decade of the century. So we know what we have to do. We have to do multidimensional simulations of core collapse supernova if we want to be able to make a statement about how they actually work. So to that end, we've written a code that we call Chimera. We call it Chimera because it's really the wedding of 3 separate codes. I think at some point we back-engineered an acronym for it, but I honestly can't remember what this back-engineered acronym is, and in any event, it's completely fallacious. We didn't call it Chimera for that reason. We called it Chimera because it has 3 heads. It takes a lot of people to work on this. In contrast with the Flash code, Chimera is written for a single problem. It is written specifically for the modeling of core collapse supernovae. And so in some ways, we don't have some of the same constraints that the Flash code has on it because we're not going to support it for open science necessarily. Parts of it, yes. Certainly the individual heads of Chimera, the VH1 hydrodynamics is used widely by lots of people. The nuclear network called XNet has probably 300 citations in the literature because it's widely used to model nuclear burning. But for the most part, the wedding of these 3 things is something that we're not going to promulgate out to the wider world. We benefit from having funding from a lot of different agencies. This is the speeds and feeds plot that only makes sense to experts about Chimera, but it's just to give you a hint about which pieces of sort of industry standard things we stick in there. Trust me, this all has meaning to various people. The 2 interesting things here are how we do neutrino transport. That is, we only can afford to do the transport along individual radial rays, which is of course a gross approximation in multi-D. But we have some good reasons to think it's not a bad approximation. And the hydrodynamics that we use is fully GR, fully general relativistic. That's important because GR gravity in general is stronger than Newtonian gravity and can have an impact directly on the outcome of the explosion. And the fact that we can only afford to use what's called an alpha network. So we do nuclear burning. There's a perfect analog in terrestrial combustion, or indeed the nuclear combustion that is necessary to study type 1a supernovae. In situ, we're only able to do 14 nuclei at a time in the network, all the way up to iron. This is a gross simplification for us because one of the things that's happening throughout the explosion is that electrons are being shoved into protons because of the high densities, and the nuclei are becoming more and more neutron rich as the explosion goes on. And you can't capture any of that with an alpha network. You can only go up in even numbers of protons and neutrons. So I can't account for the presence of a given probably highly radioactive nucleus that has a lot of neutrons relative to the number of protons it has. And that's a clear deficiency in our models, and one that we're working very hard to overcome. I'm going to show you movies from a recent publication, literally this month, where we've done a set of progenitor models that the progenitor stars of which range from being 12 solar masses in size to 25 solar masses in size, so 12 times the size of the sun to 25. I'll show you the 12. The point of the paper is to say that for that wide range of progenitor models, which accounts for 87 or 88% of all the massive stars bigger than 8 solar masses, we get the same sort of result. That is, we do, in 2 dimensions, we are able to drive neutrino-driven explosions for a variety of conditions. The top panel, in each case, it's a single hemisphere for the simulation. The top panel is the entropy. Entropy is a good proxy for temperature because the entire configuration is very, very hot. But with entropy, you can see the stuff that's more ordered or less ordered. You can easily see what will become the protoneutron star if you use entropy. The bottom frame will be the radial velocity, and you can see that the color map ends at 30,000 kilometers per second. So as Don reported to you earlier, 40,000 kilometers per second for outflow velocities when supernovae typically really are going is typical. That's 0.1 C. That's fast indeed. So let me just roll the movie. So again, the upper view is the entropy. You can think of it as the temperature. We pick up the action just after the core has bounced and the shock waves being spit out. You can see that just like in 1D, it sort of stops when it gets to some radius. Then it starts wiggling back and forth, and these convective cells are set up. Now we're going to zoom out so you can see more of the configuration. All this action is happening only right now in the inner 500 kilometers of the star. So remember, we're in the belly of a red supergiant that is probably 7 or 8 AU in size. So 7 or 8 times from here to the sun in size. And we're only looking at the inner now 2,000 kilometers of it. The rest of the star at this point has no idea what's going on. But again, the explosion's only been going for about a quarter of a second at this point. So perhaps that's not so surprising. You can see what happens is that low entropy downflows are feeding these high energy outflows, high entropy outflows. Material is being fed onto the surface of this very hot protoneutron star. When it gets there, everything is sort of blown apart. The neutrino heating that results tends to push the material out. And by the time you get to close to a half a second, this thing is well on its way to exploding and will, in fact, produce a supernova. So Don told you a little bit about validation of astrophysical results. And I want to stress that although people tend to have this picture of a lot of astrophysical simulation as being, let's say, empirical data challenged, there's in fact tons of data that come out of these simulations that we can directly compare to observations. Just like Don referred to earlier, there's of course the photons that come out of the event itself and that people here in Tucson are especially interested in. But from things like core collapse supernova, there are also other observables, one being gravitational waves. So when you take a large amount of mass and you wiggle it really fast, you produce ripples in space-time itself. And there are actually several now detectors here on the Earth that can detect these gravitational waves. Now, the source has to be fairly close. Typically, people put the source at 10 kiloparsecs, so maybe a third of the distance from here to the other side of the galaxy. The good news is we haven't observed a core collapse supernova in our own galaxy for almost 500 years now. So if you don't believe in statistics, we're due. Because for a galaxy our size, you typically should have one core collapse every century. Now, of course, that's not true. We're not due by any, because it's really a statistical measure, but nevertheless, there's hope that something will go off. We can produce templates for use in those things, in addition to guiding the experimental programs of other big experimental facilities. So one of those is this facility for rare isotope beams that is going to be built at Michigan State. So we heard about the LSST earlier, which could probably going to end up costing maybe $500 million, sort of in its first, by the time it gets built in its first year of operation. FRIB probably costs twice that, roughly. And the only way to sort of guide the experimentalists who are going to work at FRIB into what they should actually look at. So which one of these neutron-rich nuclei should they first tune their detectors to? The only way to do that basically is to do these kind of simulations so they know what the individual astrophysical objects are most sensitive to. Because nuclei this neutron-rich only occur in these sort of environments. For example, in core collapse supernovae. This is the only place we actually see them. Okay, so we've done 2D simulations. We've obtained explosions in 2D for a variety of progenitor masses. There's a problem, though. It turns out that standing accretion shock instability that I told you about earlier, when you go to 3D, instead of being dominated by an L=1 mode, a sloshing mode that sort of goes back and forth, it quickly falls into this M=1 or spiral mode. That doesn't do quite as an effective a job of pushing the shock out, getting it out of the potential well, so you can heat the material behind it and push it out. So ultimately, 2D won't cut it. We have to do three-dimensional simulations, if for no other reason, because we know the fundamental nature of the SASE changes in 3D. Never mind the fact that nature is 3D. And there's lots of other reasons. We know that fundamentally the nature of turbulence changes as you go from 2D to 3D as well. But this is the big elephant in the room. We know that the SASE is fundamentally different in 2D and 3D. So we've started those simulations, and I can show you just a handful of milliseconds, and I'll tell you why it's such a short clip here in just a second. The big 3D simulations we do typically take roughly a third of Titan, so 130,000 or so CPUs, and the wall clock time to get out to a half a second of evolution will be roughly 6 months. So we have to occupy Titan, a third of Titan, for 6 months to be able to do a single simulation of this type. Obviously, we can only afford to do a handful of those to inform our 2D simulations or lower res 3D simulations. So we're going to do the same sort of parameterization and parameter sweep that Don was referring to earlier when it comes to 1As, because we just don't have the time to spare. Nevertheless, stellar astrophysics in general has done really well in InSight. So this InSight program, if everybody doesn't know, is the primary allocation mechanism through which hours are awarded at the leadership computing facilities at Argonne and at Oak Ridge. And if you look back over the past 3 or so years, the average number of CPU hours a year that has been dedicated to projects that I would term stellar astrophysics is about 172 million a year over usually typically 3 to 4 projects each year. You can add to that things that have been very much concerned with galaxy formation, galaxy cluster formation, and galactic evolution. For example, the Via Lactea runs by Pierre Medal and others, so you can sort of add that to the overall astrophysics portfolio. But just if you want to talk about stars, and especially blowing up stars, we've sort of gotten 172 million hours a year. That's about 10% of the total InSight pot in that time, which for a single field of science, a rather narrow field of science, is pretty darn good, considering that we're competing against climate modelers, combustion modelers, fusion energy modelers, nuclear engineers. So why so much? Well, I think it's really because of 2 things. One, we formulated large, important scientific questions, and we have a track record of being able to exploit the hardware at a very, very high level. So my question is, will this trend continue in the future? Will we be able to be able to solve big problems efficiently in the future? So you might have seen this on my original slide where I said the computers aren't getting any faster, they're only getting wider. And I think somebody this morning brought up that fact that, if you move from one modern day platform to the new one and you use the same sort of decomposition, you're in fact going to be longer to solution. Well, I've talked a lot about this recently with my scientific computing hat on, and I've shown this next slide countless times. And I can't tell you how happy I am to show this slide in Tucson. Okay, this is the first page of a paper that was actually put on the astrophysics preprint server back in 1999, written by several of my colleagues. Chris Grotbath used to work for Total View Technologies for years. He was a graduate student here at the Stewart Observatory. Jeremy Balin, Casey Meakin was at the Flash Center for a while. Todd Thompson is another core collapse supernova modeler who's now at Ohio State. They wrote this paper and actually put it on the preprint server where they showed that if you would just slack off on whatever calculation you need to do, in the late 90s anyway, if you just put up what you were doing and just waited 6 months, 8 months, I think the number they arrived that you really needed to wait 40 months ultimately because of Moore's Law. If you just put the problem aside and just wait until you could buy a new computer 40 months from now, you'll be able to get to the answer at exactly the same time. Because Moore's Law will have allowed your workstation to get so much faster that there was no point in actually doing it. So you could drink coffee, talk to your friends, go to movies. You really didn't have to work for 40 months. This doesn't obtain anymore. More's the pity, because ultimately I think all of us astrophysicists are lazy and we want to get our answer as fast as possible. And of course, the biggest example of this problem, if you want to call it that, is the one that I sat right on top of, literally, the Titan at Oak Ridge, our big XK7 system. It's 27 petaflops peak, but almost all of that is tied up in those 18,688 NVIDIA Kepler K20X GPUs. So being able to tap those is what's really important. Tapping those, and Don also alluded to this, is really a problem in uncovering unrealized ubiquitous parallelism. So we all tend to do domain decomposition where we divide up the region of space, be it a star or some local part of our universe, into separate domains, and we typically parallelize those with MPI. Lots of people have learned how to use things like OpenMP to thread the loops deep in those things to be able to get a little bit more parallelism out. At the bottom of each one of those loop nests, whether you're working on a GPU from NVIDIA or you're working on an Intel Phi from Intel, ultimately you have to do something that's vector-like to be able to tap those things. So we've discovered that's really the problem, right? 70 to 80% of the work in quote-unquote porting a code to a GPU machine is restructuring data structures and loop nests so that you can uncover as much parallelism as possible. Our experience at OLCF with with a handful of codes suggests that you need 1 to 2 person years to perform this initial port. This is probably less if you began today, because when we started this, it was a couple of years ago, right? 2 years before Titan actually hit the floor, so we didn't have the set of sophisticated compilers and tools that we have now. But now we're back to good news again. The good news is stellar astrophysics tends to have lots of unrealized parallelism because there tends to be multiple degrees of freedom per spatial grid point because we put all that darn physics in there. So for the core collapse supernova problem, a good example is radiation transport and nuclear burning. So that at every spatial grid point, not only do I want to evolve the thermodynamic state of the matter that's actually sloshing around in there, I want to be able to burn at least 14, hopefully 150 nuclei at a time, and to do radiation transport on several flavors of neutrinos. Still, we're going to still continue to do spatial domains by domain decomposition. And then the last thing I want to leave you with is, if you want to do that, if you want to do multi-physics in a split way, locally bulk synchronous programming models are horrible, right? What you really want to do is something that's a little more graph-directed. I took these comments directly from David Keyes, and they'll be in my presentation, so I'll let you read those. But we've already begun exploring ways to do asynchronous execution in our multi-physics simulations. So that is to be able to bust out the thermodynamics and the transport, put those each on a node local, and to use some sort of scheduling mechanism, probably traversing a directed acyclic graph, to be able to decide which pieces of that execution we're actually going to carry out. Don't move the data, but rather move the computation to the data. There are examples already existing in other particular subfields. For example, Magma, the GPUized version of LAPACK, already does something like this on a per node basis. Madness, which is a DFT code for chemistry and material science, also is built upon this idea. And Uinta, which was the code developed at the University of Utah under the same ASC program that Flash is a part of, also is built on these same ideas. So with that, I'll just put up my summary once again and ask if there's any questions before the panel.
Thank you very much. Any questions? I can get started with one. So, did you measure out of the Titan? What fraction percentage of peak did you accomplish in terms of?
So for CPU only, our fraction of peak for Titan depends on, of course, there's a lot of pieces go into that calculus. It depends on whether or not we treat each one of the bulldozer modules as an individual core, if we treat the computing cores. If we do our best production run, we get upwards of 20% efficiency for the CPU only parts. And for the nuclear burning, which is basically the only part we put on the GPU so far, we're approaching, for some network sizes, 70% of the peak. So that's only 15 to 20% of the entire simulation. So an analog of Amdahl's law is still sort of killing us.
And the other time when you're computing, then GPU is sitting idle at that point.
That's correct. That's correct.
Other questions? Before we go into a panel, if you want to.
Hi, I was intrigued by the 1 to 2 man years to do the. Now, if they upgrade the Titan and it has the next generation, can you use that code without modification, or are you going to have to spend?
Without modification is probably too strong a statement. But again, the other thing that we found over doing that sort of survey, the one that gave me the 1 to 2 FTE years for the port, said that between 70 and 80% of the total work is the restructuring of data structures and hoisting loop nests, and hoisting things out of subroutines and changing the order of loop nests. That 70 to 80% of the work will not have to be done again. So ultimately, it's sort of it's the analog of changing to a new message passing library from MPI, right? There's a relatively small amount of code that gets touched with, for example, CUDA or OpenACC. Ultimately, they're going to be operating on the same data structures. So I think that without modification is too strong a term, but without major modification, I think it's certainly the case.